Hello everyone and welcome to Educator.com. I'm Dan Fullerton and today we're going to start a series of lessons for AP Physics C, specifically the Electricity and Magnetism course. So let's dive in by talking about electric charge and Coulomb's law. Now, some of our objectives are going to be to calculate the charge on an object and explain the law of conservation of charge. That's going to be a big idea throughout the course. Describe differences between conductors and insulators. Explain the difference between conduction and induction. Talk about polarization and inducing charges or induction. And use Coulombs Law and the principle of superposition, which is going to come up a lot in this course, to solve for the force of a charged particle due to other point charges. So with that, why don't we dive in and let's start talking about electric charges. First off, matter is made up of atoms, and atoms contain protons, which are positive, electrons, which are negative, and neutrons in the nucleus, which are neutral. Most atoms are neutral. They have the same number of protons and the same number of electrons. Their positive charges are exactly balanced by the negative charges. Now, atoms that have lost or gained electron have a net charge. They're no longer neutral, so they're called ions. Also, the fundamental unit of charge is known as a Coulomb, with the abbreviation capital C. And a Coulomb is a very, very large amount of electric charge. Typically, we're going to be talking about units much smaller than a Coulomb. Not always, but a vast majority of the time. The smallest isolated unit of electric charge is called the elementary charge, the charge that's on a single electron or a single proton. And one elementary charge is equal to 1.6 times 10 to the minus 19 coulombs. You're going to see that come up again and again and again in the course, this fundamental unit, and it's also on your formula sheet for the AP Physics C test. Like charges repel while opposites attract, probably knew that already, and electric charge is conserved. This law of conservation of charge is a huge idea again in AP Physics C, E&M. What that really means is if we have any closed system, whatever charge we start with is the same charge we're going to have when we're done. If we start with a neutral atom and we pull off 2 electrons, we have negative 2 elementary charges over here. What we're left with over here must be 2 positive 2 elementary charges, so that the sum total of the charge is still 0, is still neutral. That law of conservation of charge. So let's take a look at an example or two and see how this works out. First off, Mittens the cat possesses an excess of 6 times 10 to the 6th electrons. What is the net charge on Mittens? Well, the way I'd go about doing that is let's find the charge, abbreviated with the Q, is equal to, well, we have 6 times 10 to the 6th elementary charges, and the charge on each one of those electrons is negative 1.6 times 10 to the minus 19 coulombs, because electrons are negatively charged, for every elementary charge or electron. Therefore, when we multiply through, we're going to have our e's cancel out. 6 times 10 to the 6th times negative 1.6 times 10 to the minus 19 to give us an answer of right around negative 9.6 times 10 to the minus 13 coulombs. Pretty straightforward. Let's do another one. Let's find the charge on an alpha particle. An alpha particle, also known as a helium nucleus, consists of 2 protons and 2 neutrons. What is the charge of an alpha particle? Well, the first thing we have to recognize here is that the neutrons are neutral. They have no charge. They don't contribute any charge to the answer to our question. Instead, we need to focus on these 2 protons. So the charge, Q, is positive 2 elementary charges, which is going to be 2 times 1.6 times 10 to the minus 19 coulombs, for a total of 3.2 times 10 to the minus 19 coulombs. Again, notice our answer, how much smaller that is than a coulomb. 10 to the minus 19 coulombs. Typically, we're going to be dealing with quantities of charge that are smaller than coulombs. Not always, but quite a bit at a time. So let's move on for a moment and talk about conductors and insulators. Conductors allow electric charges to move freely. They have a very low resistivity, another term that's going to be good to know. Insulators, on the other hand, do not allow electric charge to move freely. Therefore, they have a very high resistivity. Now, resistivity is a material property. It tells you how freely that material allows electrons to move, and it gets the symbol rho, the Greek letter rho, kind of like a squiggly P. Materials that have a high resistivity, things like glass, plastic, my flannel blanket at home, all good insulators, all have a very high resistivity. Materials with a very low resistivity are good conductors. Things like gold, silver, most of the metals, typically very good conductors. So, let's talk about how we charge something. And we'll start by talking about charging by conduction. When things are charged by contact, we call that conduction. And here's a trick you can try. Rub a balloon against your hair for a little bit. Some electrons from the atoms in your hair are transferred to the balloon, an example of conduction. The balloon, therefore, picks up some extra electrons. It becomes negatively charged, while your hair, by the law of conservation of charge, must become positively charged. You can then test that out by taking the balloon and going and trying to stick it onto a wall or something like that, maybe a shirt. Oftentimes you can get it to stick, which is showing that it's charged or the wall is charged, and by common sense, you know it's probably the balloon. Conductors may be charged by contact. A charged conductor brought into contact with an identical neutral conductor will share the charge across the conductors. And we'll show an example of that here right quick. Here we have a conductor carrying a net charge of 8 elementary charges, and it's brought into contact with an identical conductor that has no net charge. What's the charge on each conductor after we bring them together and then separate them? Well, once we touch them together, if they're identical spheres, they're going to share the charge across them. Each one is going to have 4 elementary charges. When we split them apart, they each have 4. What is that in coulombs? Well, we have 4 elementary charges, which is 4 times 1.6 times 10 to the minus 19 coulombs, or 6.4 times 10 to the minus 19 coulombs on each of those conducting spheres. A useful tool for detecting charge is known as the electroscope. Basically what it is an insulating bottle of some sort that has a metal rod in it, and down at the bottom you have a couple of foil leaves, conducting foil leaves that are very easy to move. So if you bring something like a positively charged rod near the metal head, the electrons that are free to move in this metal rod try and get as close as they can. Opposites attract. When that happens, as the electrons move to the top, you're left with the net positive charge here on the bottom. And then the leaves at the bottom, because they have the same charge, tend to spread apart. So it's kind of a charge detector. We could also charge something by induction, charging a conductor without coming into contact with another charged object. And here's an example of how we might do that with an electroscope. If we start out and bring a positive rod near the head of the electroscope, the negative charges try and congregate near that positive rod. It attracts the negative charges, leaving a net positive charge down here at the bottom of the electroscope. The leaves spread apart. Now what we do, though, is we connect that metal rod to ground. And you can think of connecting to ground as connecting to the Earth. And really the Earth is like this giant sink or source of charges. It's kind of like a magic purse for any electrical charges. If you need more negative charges, connect it to ground. They'll be pulled up. If you have extra charges to get rid of, put them to ground. A great place to go store them for a while. So what we do is while we have the positive rod here but not touching, we attach the metal rod to ground, and because we have the positive charge, we want to have negative charges here. The ground wire sucks up all these negative charges, so we have a bunch of negative charges now in the head of the metal. Then we disconnect the ground wire, and the charges, the negative charges, are stuck on the negative rod, on the metal rod. Therefore, the leaves spread apart again, but it's because they are charged negatively as we bring that rod away. So we ended up having a rod that was neutral to begin with. Over here on the right, when it's done, it's negatively charged. But we never touched our positively charged rod to it. All we did was connected it to ground. So that would be an example of charging by induction. So let's take a look at some examples. A positively charged glass rod attracts object X. The net charge of object X may be, and our choices are A, it may be 0 or negative, B, it may be 0 or positive, C, it must be negative, or D, it must be positive. Well, let's think about that. If we take a positively charged glass rod and we bring it near some object X, well, if it's negatively charged, they'll definitely be attracted. Opposites attract, so that could be true. But also, if we have a positively charged rod and we bring it near a neutral object, what can happen is, if we look closely, the entire thing is neutral, excuse me. But when we bring the positively charged rod near it, the atoms that are nearest the rod, the electrons on those atoms, are attracted to the positive rod. So what they'll do is they'll actually spend a little bit more time orbiting the nucleus over toward the positive rod. So we have just a little tiny bit of a shift in the material, with the electron spending a little bit more time on this side of the nucleus than this side. That gives us a net negative charge over on this side of the object, and we can still get attraction. So a charged object can attract a neutral object. So we know that the answer must be 0 or negative. The only way to prove two objects are charged is repulsion. You can charge a neutral object with a charged object. If you want to prove that they're both charged, they have to repel. This, by the way, is known as polarization of those atoms. The whole thing is still electrically neutral, but because the electrons spend a little bit more time over here, you get a little bit stronger force of attraction than you do repulsion, and a net attraction occurs. Let's talk about that a little bit more. When a charged object is brought near a conductor, the electrons in the conductor are free to move. But when a charged object is brought near an insulator, the electrons aren't free to move. They spend a little more time on one side of their orbit, creating a net separation of charge known as polarization. Now, the distance between the shifted positive and negative charges multiplied by the charge is known as the electric dipole moment. And here we just have a couple diagrams showing that. With the conductor, a charged rod, and a conductor, the electrons spend time here. It's easy to see the attraction. With the charged rod and insulator, where the charges aren't free to move, inside the atoms themselves, the electrons spend a little bit more time toward the positive side, and you still get that net force of attraction. So we've been talking about this force of attraction and repulsion between charges. Let's go formalize that a little bit and see if we can't calculate it using what's known as Coulombs Law. Charged objects apply a force upon each other, known as the electrostatic force, or sometimes called the Coulombic force. Similar to gravity, the force of attraction or repulsion is determined by the amount of charge and the distance between the charges. And it's actually another inverse square law. It goes as the inverse square of the distance between the center of those charges. So if we have charge 1, Q1 over here, Q2 over here, the magnitude of the force between them can be found by taking some constant, some fudge factor, K, times the first charge in coulombs, times the second charge in coulombs, divided by the square of the distance between their centers. And be careful here, we're using R as the distance between the centers of the object. In this case, we're not talking about a radius itself. R is the distance between their centers. And when we do this, we end up with a K constant of roughly 9 times 10 to the 9th Newton meter squared per Coulomb squared. All right, notice how similar this is to the force of gravity. Universal gravitational constant times the first mass times the second mass times the square of the distance between them. Other than the K and G, a different fudge factor to make the units work out right, you have the same form. They work in a very similar manner. The other big difference between gravity and the Coulombic force, however, is that the Coulombic force can repel, whereas gravity only ever attracts. So let's take a look at Coulomb's law now in vector form. Here we have charge 1 and charge 2. R12 is the vector from 1 to 2. And we're also going to define a unit vector in the direction from 1 to 2, which we're going to call R hat 1 to 2. And if these are both positive, what we'd expect is a force of 1 on 2 repelling it over to the right. So writing that mathematically, the force of 1 on 2 is equal to our fudge factor, K, 9 times 10 to the 9th Newton meter squared per Coulomb squared, times the magnitude of the first charge, the magnitude of the second charge, divided by the square of the distance between them. And the r hat 1, 2 is just saying the direction. It's from 1 to 2 on the direction of that line. Another way to write this is we can take this k and write it as 1 over 4 pi epsilon 0, the permittivity of free space. So 9 times 10 to the 9th or 1 over 4 pi epsilon naught are the same thing. We're going to use this form of that fudge factor quite regularly in the E&M course because it's going to help us with some derivations later, but really they're the same thing. This is a constant, this is a constant, they have the same value. Where if we write it this way, epsilon 0 is 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. And k is equal to 1 over 4 pi epsilon naught. So if you're ever doing these calculations and you see this, easy enough to just swap in k for it if you want, 9 times 10 to the 9th. Or if it looks like you can maybe cancel a pi or an epsilon naught, go from k that way. They're the exact same thing. All right, determining the electrostatic force. We have 3 protons separated from a single electron by a distance of 1 micron. So 3 protons plus 3 elementary charges separated from a single electron minus 1 elementary charge by a distance of 1 micron, or 1 times 10 to the minus 6 meters. Find the force between them, and is it attractive or repulsive? Well, let's do the easy part first. Attractive or repulsive? They're opposites. They must attract. All right, let's find the magnitude of that force. Our first charge, Q1, is 3 elementary charges, which is 3 times 1.6 times 10 to the minus 19 coulombs, or 4.8 times 10 to the minus 19 coulombs. Our second charge, Q2, is the charge of our single electron, which is minus 1 elementary charge, or minus 1.6 times 10 to the minus 19 coulombs. And the distance between them is 10 to the minus 6 meters. Therefore, when we go to find the electrostatic force, that's going to be K, Q1, Q2 over R squared. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared, times Q1, 4.8 times 10 to the minus 19 coulombs, times Q2, negative 1.6 times 10 to the minus 19 coulombs, all divided by the square of the distance between them, which is 10 to the minus 6 meters squared. And when I go through and do my math, plug that into my calculator, I come up with something like the electrostatic force is about equal to 6.9 times 10 to the minus 16 units are newtons, and of course that must be attractive. All right, moving on. A beam of electrons is directed into the electric field between 2 oppositely charged parallel plates. What is the direction of the electrostatic force exerted on the electrons by the electric field? Well, let's see. Our electron beam is actually going to be just a bunch of electrons traveling to the right. Now, as the electrons travel to the right, they're negative charges. They see the positive charge up here. They're going to feel a force toward the positives due to this plate. And down here they see a negative. They're negative. They're going to be repelled. That's also going to push them in the upward direction. So our net force must be up. Let's see if we can't put this together into a slightly more involved problem. We have 3 point charges located at the corners of a right triangle as shown, where Q1 and Q2 are both 3 microcoulombs, 3 times 10 to the minus 6 coulombs, and Q3 is minus 4 microcoulombs. If Q1 and Q2 are each 1 centimeter from Q3, find the net force on Q3. All right, well, let's start by looking at the force of 1 on 3. We'll call that F1 comma 3, and that's going to be equal to K Q1 Q3 over R squared, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared, times our charge on Q1, 3 microcoulombs, or 3 times 10 to the minus 6 coulombs, times Q3, which we said was minus 4 times 10 to the minus 6 coulombs, and I'm just going to work with magnitudes for now and figure out the directions when we're done, divided by the square of the distance between them. 1 centimeter is 0.01 meter, and we have to square that. So I end up with about 1,080 newtons when I plug that into my calculator. And we're looking at the force of 1 on 3. If this is negative and this is positive, we're going to have a force upward on 3 due to 1. So that's 1,080 newtons up, or I could write that as, in unit vector notation, 1,080 newtons in the j-hat direction. All right, let's take the look at the force on Q3 due to Q2. So the force of 2 on 3 is going to be KQ3 Q2 over r squared, which is going to be 9 times 10 to the 9th again, times our first charge, 3 microcoulombs, 3 times 10 to the minus 6, times our second charge, 4 times 10 to the minus 6, all over the square of the distance between them again, 0.01 meters squared, or, again, 1080 newtons. But as we look at this one, we have a positive charge here, a negative charge here, so the force on 3 due to 2 is going to be to the right. So 1080 newtons to the right, or 1080 newtons in the I-hat direction, in the x direction, unit vector notation. So if we want the total force, we'll use the law of superposition and just add these together. That's going to be, we'll have this component, 1,080 newtons to the right in the I-hat direction, plus we have our 1,080 newtons in the j-hat direction. Or if you wanted to write this in component form, that's just 1080 newtons in the x, 1080 newtons in the y. And if we wanted to know the magnitude of that force, well, we have 1080 newtons up, 1080 newtons to the right. This makes a right triangle. We can use the Pythagorean theorem to figure that out. The total force then, the magnitude of that total force, is going to just be the square root of 1080 squared plus 1080 squared, or about 1527 newtons. And the direction, that's going to be at an angle of about 45 degrees, of exactly 45 degrees north of east. Something like that, 1527 newtons. 1 to the right, 1 up, the combination, something like that. All right, let's take a look at one last example here in this lesson and see how it goes. Putting all of this stuff together, we have 2 identically charged balls of mass 5 milligrams hung from the ceiling by a light string of length 20 centimeters. And when we say light string in physics, that means you can neglect the mass of the string. It makes life a whole lot simpler. The total angle between them is 12 degrees. Find the magnitude of the charge on each ball. All right, well, the first thing I'm going to do is let me draw in a little bit here. I'm going to draw a center line between these, just so that I can see what's going on here. And I'm going to call the angle right there theta. And if the whole angle between them is 12 degrees, this theta is 6 degrees, and that theta must be 6 degrees. And let's call this ball 1 and that ball 2. So if we start from there, I always like to look at free body diagrams to help me identify forces and what's going on. So starting with the free body diagram, let's look at the ball on the left, ball number 1. We have our object, which I draw as a dot. Our forces on it, we have its weight, mg down. We have the tension from the string, T. And we have the force of electrostatic repulsion to the left, Fe. But I have a force at an angle, and that always makes things more complicated. So what I want to do is break up this tension into components along the x and y axes. So the way I'm going to do that is I'm going to redraw my free body diagram to make a pseudo free body diagram, where I still have mg down. I have the electrostatic force to the left, but now I'm going to break up this tension into a component that is vertical and a component that is horizontal. And looking at my angle here, or if I were to look at it here as well, it's pretty easy to see that the component to the right is going to be t sine theta. That's opposite our theta. And this component, the vertical component, will be t cosine theta because the horizontal is adjacent to our angle as we've defined it, theta. So now I can start writing Newton's second law equations to solve the problem. Let's start with the net force in the x direction. I can say net force in the x direction. Then I just look at my pseudo free body diagram and write in all the forces in the x direction. I have t sine theta in the positive x direction, and I have the electrostatic force in the negative x direction. And because this is in equilibrium, it's not accelerating, I know that the total must be 0. Therefore, I could write then that t sine theta must equal the electrostatic force. All right, there's one equation we can use. Let's try the same thing with the y direction. Net force in the y direction equals, and now I look at my pseudo free body diagram again, I have t cosine theta in the positive y direction minus mg. And again, it's not accelerating in the y direction, so that must equal to 0. Therefore, I can state that t cosine theta must be equal to mg. I've got my two equations. Looks like I can probably do some simplifications here. And I'm going to pull a little trick. As I look at this, if that's equal to that, and that is equal to that, if I divide the first equation by the second, that also still has to be equal. So t sine theta over t cosine theta must equal Fe over mg. Let's write that. T sine theta over t cosine theta must be equal to our electrostatic force divided by gravity. T over t is 1. Sine theta over cosine theta is the tangent of theta. So this implies then that the tangent of theta equals Fe over mg. Or I could rewrite this to say that the electrostatic force equals mg tan theta. But the electrostatic force we can get from Coulomb's law. That's equal to K Q1 Q2 over R squared. Q1 and Q2 are the same. These are identical spheres, so this is just Q and Q. But the trick then is this R, the distance between them. We could figure that out. This implies then we know the length of the string and we know the angle. We can use a little trig to realize that the distance from here to the center point must be L sine theta, this 20 centimeters sine theta. So the distance between the first and the second sphere must be twice that. So our R must be 2 times the length of the string sine theta. So if I rewrite this again, we could say that K, Q1 times Q2, if they're the same thing, just Q, that's KQ squared over R squared is going to be 4L squared sine squared theta must be equal to mg tan theta, which implies then that our charge itself, rearranging this and solving for just Q, must be equal to the square root of 4 mg L squared sine squared theta tangent of theta all over K. Wow, that's quite the equation. So let's substitute in what we know to say that Q must equal 4 times our 5 grams, 0.005 kilograms, times g, 9.8 meters per second squared on the surface of the Earth, times our length, 0.2 meters squared, times the square of the sine of our angle, which is 6 degrees, times the tangent of our angle, 6 degrees, all over 9 times 10 to the 9th, K, Newton meter squared per Coulomb squared. Take the square root of that, and I come up with about 3.16 times 10 to the minus 8 coulombs. The charge on each of those spheres. Hopefully that gets you a great start on electric fields and Coulomb's Law, electric charges and Coulomb's Law. Come back for the next one, and thank you very much for watching Educator.com. I'll see you again real soon. Make it a great day.